And and we also look at a general structure of bipartite entanglement, in particular the Schmidt decomposition, which follows from singular value decomposition of the coefficients when you have two entangled system, right? So say normally if I use product basis, so a basis element that are themselves tensor products, then I will need to have two indices to sum over two indices here. But by applying Schmidt the singular value decomposition, we have a special way to write this. Right, where these are orthonormal bases in the respective space. And to be correct, so the number of term in the sum is basically the rank of the matrix that we do the SVD, or equivalently is the number of non-zero singular values. Right? And this is at most, I'm not sure if last time I wrote equality sign here, but the J is at most the minimum dimension. Of the two Hilbert spaces. But it can be less than that. So to be precisely correctly, I can say that these are in O and B, but some of the PJ can be 0. But those will, I mean, ultimately wouldn't matter, wouldn't impact the sum. And in particular, a very special result is that now this is in the Schmidt form, you can basically get the eigenbasis of the reduced density matrix of either of the system easily, because these already are small, right? And then you just do the partial trace. Yeah, for example, the density matrix of the reduced density matrix of party A would just be this, and the spectrum here, you can see that whether I reduce it to system A or B, the spectrum here, the eigen values here will still be the same. Also, since we know, I think it's worth emphasizing that since we know that the reduced density matrix is basically the complete information that you can have for any subsystem, right? So whatever you measure here, if you only measure in a single system, then the density matrix is all that you need. And so from here you can sort of see, right, that entanglement cannot be used for instant communication or faster than light communication, precisely because yeah, for example, any unitary that, for say, if I apply any unitary operator here on system B, it doesn't affect the reduced density matrix of A in any way. Yeah, the spectrum will still be the same. The probabilities will still be the same. Right, and we will yeah, come back to this maybe a couple of lectures later. But for now, oh, and if you have any comment, discussion, something that you curious about, yeah, please ask me anytime, right? Quantum circuit diagrams or notations. So there's just some tools that will make it more convenient to talk about or think about multipartite system. Okay. So who haven't seen quantum circuits? Have you seen quantum circuit before? Oh, I see. Yeah. So basically, it's a way that, for example, if I have well, not for example, when I have multiple quantum system, multipartite quantum system, well, then system A, system B. So for example, let's say I can have like a bunch of Hilbert spaces come together, right? And then I can consider states in this vector space, in this Hilbert space, and consider operation applying to them. But to do everything algebraically is sort of a mess. And the quantum circuit way is sort of that I represent time and space at in orthogonal directions. uh, for example, if I have like 3 systems or more, then I can represent time evolution of each, or like the identity operation of each system as a wire. And for every linear operator that you apply to the system, say if you apply is a linear operator on only on the first system, then I can write them as some kind of box that you can label to, you know, to tell people what is actually the operator that you apply to. Or you can also apply operators that has support in more than one system, like this. Right. And so, for example, if I have something like this, so the quantum circuit has a bit of a topological property that you can sort of slide, the notation suggests that you can slide the wire in anywhere you want, as long as you don't hit the other operation, right? So for example, let's say this is case B, let's say A, B, C, D. This here means that I apply A on system A and C on the third system at the same time. Well, and maybe if I want to, you know, order the Hilbert space correctly, maybe I say I don't do anything to Hilbert space B. I do this and so on if I have more system. But from here, you can also see that since operation on different Hilbert space always commute, I guess this is clear, right? That say if I have something like this, the commutator would be 0, just because either way that I multiply it, I just get A tensor B. Right? So for here, from this you sort of know that the order, for example, if you consider B, the operation B and C, the order of them doesn't really matter because they act on different system. But operators that act on the same system, like A and B or C and D or B and D, you cannot change the order of them without changing the operation themselves. Okay. And so for quantum gates, so when people say quantum gates, they would mean a unitary operation. That you can apply in circuits. So for example, single qubit quantum gate, an arbitrary single qubit quantum gate would just be some rotation on the Bloch sphere, right? Which would be specified by 3 parameters, because you need 2 parameters to specify the axis of rotation, and then another one the angle of rotation, right? But then if you go to like 2 qubit gates of unitary operations that can act on 2 qubits at the same time, then the complexity kind of blow up there. I think you have like 15 parameters. Right, and those like 15 are just the way that I count the number of parameters of the number of real parameters in the matrix, right? Right. How would you actually count that? 15 15 Yeah, so yeah, I realize thinking of the unitary constraint in my head is sort of difficult to see it is 15. But it's like for example, the dimension of the Lie algebra of the spatial unitary group is well known as n squared minus 1. But maybe you can try to think in your free time how you would count the number the easy way. Well, I guess thinking about it in terms of Lie algebra is the easiest way, because instead of thinking of the unitary constraint, now you think of unitary as anything that you can get by exponentiate the Hermitian operators, and then you count the dimension of Hermitian operator instead, which we already know is d squared. But okay, so jargon. So the unitary group on dimension n, this is not n qubits, by the way, right? Because if I have small little n qubits, then the dimension is 2 to the n. So here, so usually big N is 2 to the little n. And these are sort of, okay, so all possible unitary matrices or unitary operators that act on Hilbert space of dimension n. But sometimes people will talk about this spatial unitary groups, SUN, and this S that you can find in other places as well, like spatial orthogonal group, is the condition that the determinant of this matrix is 1. So as a Lie group, this is dimension n square. This is dimension n square minus 1. And well, why? Because you can think of, since a unitary matrix is always diagonalizable, right? So you can think of the eigenvalues. And the constraint here, so the determinant is the product of all eigenvalues, right? So you only need to change one eigenvalue to fix to satisfy this constraint. And here is kind of arbitrary, and it reflects the fact that global phase is unphysical, right? So you could change, right? So if I And you saw this in the last homework, the second homework as well, that I can think of a unitary, for example, for 2 by 2, so like qubit unitary gate. So I will have this guy, right? But then I can put in some arbitrary phase, and that's you get that from exponentiating the identity matrix. But since this phase is independent of the state that you apply to, then you can always ignore it by setting it to some value in here. So this is just one way to do it. Right. For example, I can have X, Y, and Z gate. I mean, here is something that you already know. I want to move it a little bit to this side. X, Y, Z. And I think we did this before, but in terms of rotation, the Pauli matrices are equivalent to rotation by pi on the Bloch sphere up to a phase I. So for example, here is I times this, and so on, right? So you just change the generator from X to Y to Z. And for example, a rotation by C, the convention is that the convention is to write these like this, right? And the 1/2 here is kind of important. So do you see why there's 1/2, 1/2 here? The matrix form, so here we sort of say that it's a rotation by phi, right? And the matrix form will be this, right? So I just replace the value of right, the value of z. Well, I just put the corresponding eigenvalue in the exponent, right? However, why people would call this a rotation by phi is just because I can pull out this phi/2 phase so that the relative phase between the 0 and 1 state is phi. So for example, in quantum computation, there would be there are T gates, and this is so T gate is the fourth root of Z, I think. So if I take a square root of phi, so this is I pi. I need pi/4 here. But in the literature, people would call this the pi/8 gate just because of that reason. And of course, I can write a compact way that this matrix acts on computational basis as well. And by computational basis, it is just a jargon that means 0, 1 basis. So here I would change the value of bit by 1 bit flip, right, for example. And for Z, I would just put the phase in front that depends on the value of Z. And no one wants to do Y, but it's just you just do both at the same time. The Hadamard gate that you have seen you have worked out in the homework, right? This is pi rotation about the direction that's in the middle in between X and Z. So let's see, I can is of course a unitary matrix because the two columns are orthonormal, right? And so what this does is that is okay. So I'm rotating around this axis, right, between X and Z. And so if I rotate by pi, then it's exchange the eigenstates of X and Z. For example, if the initial state is 0, then I just rotate it down to the uniform superposition, the plus state, right? And there are, well, one comment is that if you, so the effect of this is to change the interchange of the X and Z basis, right? But of course, there are many metrics that interchange X and Z. I can say, right, for example, I can just rotate by 90 degrees here. The special thing about the Hadamard gate is just that because it's defined such a way that it's a pi rotations, it's square to 0. It's a square to the identity. So it's the same as the Pauli matrices, a square to the identity. Right, because if say if I define some metrics that actually we can define it, so in the literature, the S gate or the phase gate, this is basically square root of C defined to be this. Let's just take the square root of -1, get I, and this is a rotation by pi over 2 on the block sphere. And so I would need to apply this 4 times to return to the original state. Right, and I can write the algebraic identity involving the S gate as well. just writing down for you to see it is not that important yet in this stage. Let's see. Oh, sorry. So, okay. Right. And this this is a square thing that I talk about, right? That over there, well, usually when I change the basis or like apply unitary to an operator, then I would need an inverse on this side, right? But I didn't put it because the inverse is h itself. But here, really, I did it. This is switch the x and y basis, although it's add the minus sign here. And of course, the action of the escape in in computational basis is just the eigenvalues to uh, 0 or 1. Maybe the most important common feature that these few gates I introduced is the fact that the conjugation of Pauli matrices with these gates also produce some other Pauli matrix. So if I conjugate Paulis by Paulis, and of course you just uh, use the algebraic multiplication rule that you know, right? And you get another Pauli. It may not be the same one, but or I can have like minus sign in front, for example. But for T-gate, it's actually not the same. So YC. This you get a linear combination of Paulis. And of course, the T-gate is a rotation around the axis, so it doesn't change the Z-axis. So in particular, this is an example of non-Clifford gate, the T-gate. Or to say it another way, which is probably the way that I should have said it, is that the defining property of what people call Clifford gate or Clifford circuit is that there, when you apply, or mathematically when you conjugate a Pauli metric, you get some Pauli metrics back. And it turns out, so for Clifford gates plus, how do I write this? It turns out we're not gonna talk about it this semester because it's a subject of quantum computation. But it turns out that this very special property of preserving the Pauli group or the set of Pauli matrices allow you to basically classically simulate, so have a compact or efficient representation of this kind of computations that you can run in a classical computer quickly. And so the converse, maybe the converse to that is that if you only have these elements in your computation, then you cannot do a universal quantum computation. So whatever you do will, you cannot do better than classical computers. And so often in the news, like quantum computation, they would usually choose the set of elementary like logic gate, but in the quantum analogs of logic gate, right? they would choose Clifford Gate and one non-Clifford Gate is usually chosen to be the T gate. So by the way, yeah, Clifford Gate is generated by, so this is just facts, right? Just statements generated by the phase gate. So square root of Pauli, the ability to change bases between Pauli's, and something which I just talked about in the second called control not gate. Any question at this stage? Okay. For multiple qubit gates, actually we just only talk about 2 qubit gates. So it can be any, by definition, it can be any unitary matrix, right? So it's like a 4x4 unitary matrix or spatial unitary matrices. But a common kind of, a common class of gates, or how you divide gates, is the so-called control unitary operations. Or just call it like control U. And in the circuits, we have this graphical representation. And here is means that if the control qubit is in the state 0, then I apply U to the target qubit. Sorry. If the control is 1, then I apply U. If the control is 0, I don't do anything. Sorry. Do nothing. And so the matrix form of this is that, well, here I have 4x4 matrix, right? And the way that I order the basis here is by the lexicographical ordering, like the dictionary ordering, right? It's called the dictionary ordering because I would run over the first alphabet first, right? I will fix the first alphabet and then I run over alphabet in like other position, and then once I run through like all the alphabets in other position, and I change the alphabet of the first position. So here, when the control is 0, I do nothing. So obviously this is the identity in this part. But then in this block, when the control qubit is 1, then I apply a single qubit gate U. And of course, over here, all the matrix element otherwise is 0. The way that you would write this in direct notation, and you can try to see why this is true, is this. The famous one is, of course, the C not gate, control not, C not. Here just refer to poly X because it's flip the value of the qubits. So if you think of this as like a classical logic gate, right? X is not, and control not has this graphical representation where the first qubit is the control qubit. If you want to switch the control and target, then I would just draw the line up from the second wire. So of course, here is the matrix form. And the action on the computational basis is, of course, that if, well, maybe you can already translate that, you add whatever value of A to the second qubit, the second register. And we can think about the inverse as well, but here it's kind of obvious because x squared is the identity. So C naught square is the identity as well. And this translate to circuit identity like this. Another gate is control Z or C phase. Control phase. So the naming here is a bit inconsistent because it's not a control phase gate, but it's a control Z. And the notation is like this. So maybe let me write this down first. So yeah, let's just for clarity, I can write this. But this is equivalent, or it's just a notation for this control Z. Of course, since both the control and the operation that you apply is diagonal in the Z basis, so the whole matrix is diagonal here. And what a consequence of the form here is that it is symmetric in the control and target qubit. Because whatever happens, right? So the only non-trivial action in the computational basis is when both of the qubits are 1. And so you can exchange the role of the target or the control qubit symmetrically, and that's why this gate is written in this way. It doesn't have a direction. Okay. Yeah, usually I would be just too lazy to write C phase, so I just write CZ. Again, because poly Z is square to 0, square to the identity, so this square to 1 is an inverse of itself. And the action on the computational basis is just put the phase depending on the product of A and B, right? Because this give the correct phase. It's the only case that give the -1 phase is when A and B are both 1. There are also gate like swap. And what this does is just that in whatever in any basis, it's just swap the state of the two qubits. So how would you write the matrix form of this one? So let's see, let's do it in the, can you do the motion again? where do you put one in the air? Wait, what is the first element here? Which one? Right here?
Yes.
Second row, one is first column. Well, you can check, right? Because this is the set 0, 0, so it shouldn't do anything, right? Yeah. So here, maybe you can already see from the way that we label the basis, I just switch the two values here. Okay. Yeah, I guess that's maybe all of the gates that I want to introduce here. And the purpose of introducing these guys, right, is that now we can start manipulating the circuit, where manipulating in a sense that we'll derive some sort of graphical rule that correspond to like algebraic identity, right? So usually without the circuit, you just like multiply 2 by 2 or 4 by 4 matrices together, or use some spatial properties here. We just do it in the form, the graphical form. So for example, I can write any single qubit identity in terms of circuit, right? So for example, if let's say I multiply C and, oh, sorry. Yeah, this is the annoying thing because the times goes in this direction. It means that, for example, if I have Zx here, it means algebraically that, yeah, because here in the algebraic notation, I apply the matrix on the right first, but here I apply the gate on the left first. So here Zx, because it's in the correct cyclic order, this is just Iy, right? For example. And so all of the algebraic identity that we saw, like on this side, like sandwich identity written in this way, here, right? So there are two cases, so two cases or two terms, right, in the control. So if in both cases, if I put x over here, I flip the bit here. Right? And then, yes, I guess let's do both cases at the same time. And this is, for example, the same as this. So now you change the definition of control. And now instead of 0 being doing nothing, now it's 1 that is doing nothing. And people have a symbol for that, which is to have an open dot on the control. Well, so now what is happening here, right? This is saying that whether the control qubit is 0 or 1, I will just apply x on the second y anyway, right? Another exercise is that now I'm trying this as well. So from x equal minus ax, then I can pull this, and then there's something about minus a within here. And well, do you think that this is correct?
Acting some C face.
So you can just get
Yeah.
no.
Sorry. Yes. Yes. No.
So what happens here is that here it gives the -1 phase only when the control qubit is 1. It's not right. Yeah. Otherwise, when the control qubit is 0, there's nothing here, and so you have a control -1.
So which one?
So it's like a control. You can say equal phase. That's not what people call control phase, because it's given equal phase to every state.
Yeah.
So what is this guy? Is just doing nothing and then applying the phase here when the control qubit is 1. Here you may recognize this as when I forgot to talk about the Kronecker product. But this is
Yeah.
So here to go in this direction, we use something called Kronecker product. This is one way, the usual way to represent the matrix form of a tensor product of matrices, and essentially depends on the way that we ordered product. Because usually there's no natural order, but if we choose the lexicographical order, then the chronicle product is that if I have a tensor B, then so suppose I will write in terms of, for an example of 2 by 2 matrices, I have the matrix element here. So I have a 4 by 4 block matrix, which the element which in the block is just all the elements of the matrix B and multiply by one of the elements of the corresponding part. Did I get that correctly? So here, the other guy is just identity, and then so in this case, every B is just the identity, and then I have matrix element of Z, the diagonal. So here is Z to the 9. And so here we're saying, remark is that C naught also preserve all these. Right, because when I conjugate it probably by C naught, so on either wire, I have at most a tensor product is always bad. Another identity which I don't know if I will assign you a homework or not, but doesn't matter. Just prove it here. In the following. This way, zigzag way of doing 3 components is to swap it. Why it is? Well, we can work in any convenient basis, right? And so, for example, I can work in the computational basis. So, if I have an input product state, A and B is just 0 or 1, at this point, this point here, the state will just be A, and then I add the value of A to B when I want to. Now, once I do another sequence, but in the opposite direction, then I have to add the value of the second register to the value of the first register. If I do it again, we can use different colors. The end result is now I add this thing back. For addition mod 2, if you add anything even number of times, then they're just 0. So in this computational basis, you have to swap the value of 2 registers. And then you extend by linearity that immediately it works the same in linear combination.
Any questions so far? For measurement, usually the notation like this at the end of the circuit is preserved for the z measurement. So in the measured in the computational basis, or we can try to, if I want to put the z in, I can try to make some symbol that distinguishes it from other gates. For example, maybe some people bases. And so now if I want to make measurement in other bases, then I can write it maybe something like this. Right? Measure in the x basis. Example circuit, for example, fail state. To create the fail state, we can name this 0011. If I want to create other fail state, I can create this state first and then apply Pauli to one of the qubits, and either one is fine. So usually the convention for writing a circuit is that you start your computation in computational basis. 0 or 1 usually you can just set off 0. And for quantum computation, this sort of convention is there to sort of prevent you to hide the computational power in the state at the beginning. For example, you could put in an, well, if there's no restriction, you could put in an arbitrary entangled state, which would usually require, like in real life, you would have to prepare giant entangled state by first having your qubit initialized in some state, right, independently. And those would be so the whole thing would just be product state, and then you have to apply a big unitary to create a giant entangled state, and then you have some computational cost or experimental cost. And if you want to count the resource correctly, then you shouldn't. You should be careful not to hide something, some complexity in the final state or the final measurement, for example. And maybe, maybe I can think of, well, why not allow myself to start the computation in an arbitrary product state, okay, like here. But then you get into some case where a product gate has can boost the computational power. For example, the T gate that we just said that if all the other gates are, if I start in a computational basis, all the other gates are from Clifford, the gates that preserve the Pauli set of Paulis, right? Then the circuit would be, we can simulate the circuit classically, efficiently. But if you add the T gate, or actually any gate that doesn't preserve, doesn't compute Paulis into Pauli, then promote the circuit or the computation to universal quantum computation, which means it can simulate any reasonable quantum process. But the T-gate is just a single qubit gate, right? Especially so the way we do we write down is a pi over 8 gate, so it's e to the pi. So it's called pi over 8, but we say that the gate is actually pi over 4. And so if I allow an arbitrary product state here, then I can, for example, like just put this state or put some state that generated by the T-gate in front, like on the Bloch sphere. So like any state on the Bloch sphere with an arbitrary angle, really. But by doing that, sometimes in some case you would be hiding the power like T-gates in the initial state, for example. So the convention is just to start everything in the zero state. I probably have to say this again in the next semester when we talk about quantum algorithm. But here, I just want to create a Bell state. This circuit would accomplish it. Okay. Because first, the Aramat gate interchange the eigenvectors of z and x. So state 0 become a superposition state, 0 plus 1. Right? And then now, since the control qubit is in superposition, so it does both operation to the target qubit at the same time, which is to do nothing. And then the other one is to flip the bit 0 here to 1. And so you get the Bell state here. Same as Bell measurement. So the way that you can write down Bell measurement is simply to just write the inverse circuit. The inverse of that circuit, and then measure in computational basis. The difference between the state and the measurement, of course, is that this one circuit, I can only create one state deterministically. But here for the measurement, I have 4 possible outcomes. 0, 1, 0, 1, that's corresponding to 4 orthogonal Bell states. Okay, so describe teleportation protocol to me. So first, how many qubits do we have? Sorry, what did you say? 3. Because you need an entangled pair and a state that we want to set. Okay. So spatial case, so here I'm not going to start in a 0 state, right? It's the state that we want to set. And now we're supposed to entangle this first, so I just copy that circuit here. Okay, so now I have pre-shared Bell state. Then, well, I just made the Bell measurement here. Yeah, actually, there's probably many ways to write this. I made the Bell measurement here. Well, I can just use decimal basis measurement. Draw this. And then now this turn the state of the third qubit to be some state that's related to psi, but it depends on the measurement result. It's psi, and you apply some x or z, right? So while the last wire has to do some correction from the information from this, and usually the convention so after you make a measurement, you turn qubit to a classical bit, right? And the convention for a classical information line is to write this double line, which I sort of did last time already. And then use this to control. Okay. Which one do I want? I don't know. Maybe this is the correct one. So you use one bit to control whether you want to apply x or not, and you use the other bit to control whether you want to apply z or not. If this is correct, you should after the correction, you should get the state psi back. I think in the fourth homework there will be some problem about the circuit. So I thought we would spend more time, but we come closer to discussion about quantum eraser. I'm not sure if you have you looked at quantum eraser or not. Okay, we need to talk about this first. So, let's see what sample should I give. Yeah. So suppose that I want to control. So this kind of thing, you could call it classical or I don't know, incoherent control. Because you are doing control. So here, the dot here, the black dot here is exactly the meaning of control. Right? It's just that now we have a classical bit instead of a qubit. So this is sort of a classical control in contrast to quantum or coherent control, where where we just define control unitary without collapsing anything. The principle of different measurements says that whenever we have a measurement in the middle of circuit, and this measurement can be used to do classical control, for example, to other wire in the circuit. We can always move the measurements to the end of the circuit. Measurements to the end of the circuit, and then replace the classical control by just qubit control line. I will draw the diagram in a minute. replace the classical control line or wire by qubit control line. And by this line here, I mean the vertical line. The vertical line connect the control and the target qubits. So the picture is like this. If I have some measurement in the in the computational basis, so if you want to make measurement in a different basis, I can apply change of basis first, right? Or actually like just sort of conjugate the measurement, but here it doesn't really make sense because I cannot put the conjugate out there. Let's say I have measure and get some classical bit out, and I use it to decide whether I want to apply U on the order system. This is the same as just do control U and then make measurement at the end. But well, the measurement at this point doesn't really do anything. You don't need this measurement to do the control anymore. And so the usual assumption is when people draw quantum circuit, they just assume that every line at the end there is a measurement, but you don't need to write it because it doesn't really matter. So here, how to prove this? What do I need to prove? So here, yeah, I guess we can do it just directly. So here, if I have superposition state of the first qubit, and then I measure it, then well, there'll be two cases, right? That with probability alpha squared and probability beta squared. With this, well, I do nothing. Yeah, so let's write the whole thing. This is psi, and then I just put phi on just some state in the computational basis, say. Well, if I can put anything in the thing, it doesn't matter. Fine. Then this I have measured out. So maybe I can say that I have collapsed the state to zero, even though, in reality, we have to see if the qubit is still there. Right? So either we collapse them or we just disappear and poof into the classical bit. But here is maybe assumed like this, and then in this case, I do nothing here. In this case, I apply U psi. On the other hand, if I do this, and then just for the sake of what we're gonna do, yeah, we say that yeah, we make measurements because why not? Here, at this point before the measurement, I will have a coherent superposition. And then now, if I measure, maybe you can see it already, if I measure the first line, the first qubit, then I get exactly the same thing as the circuit, the first circuit. Because with probably alpha square, I collapse the state to this term, probably beta square, I collapse the state to that term. Usually, measurement always assumed to happen. Assumed to happen at the end of every qubit line. And therefore, measurement after the circuit is usually omitted from the diagram, so you just don't draw it. Omit drawing the measurement box or this kind of measurement thing line at the end of the circuit. Uh, 4 minutes left, which is perfect because I sort of don't want to start talking about quantum eraser yet. Maybe we can start saying something and continue also then next week. But any questions so far? Anything? Yes. So, this sort of an optional topic for fun. Yeah, so we're gonna, well, at least next week, we're gonna use this quantum circuit to play around to understand something people talk about. Well, I guess quantum eraser, people have been talking about this even before quantum information is recognized as a field. It's kind of like quantum foundational, quantum thinking thing that people who, 50 or 60 years ago, they didn't care about losing their job and they didn't know all this kind of stuff that doesn't really do anything. That comment doesn't mean to be degrading in any way because quantum information started from people that's doing things that other people don't find it worth they are doing, but it turned out to be something. So here, so interference is, so maybe to set the stage first, I guess. So I just want to talk about difference between coherent superposition and incoherent mixture, convex combination in mixed state. So something like this. So one hallmark of quantum mechanics is that this superpositions allows interference, right? For example, at the classic example, I have a double slit experiment, and I maybe create some electron beam here, or if you want to be really quantum, then you just send electron one at a time. You don't want to think macroscopic abstract way. But then the wave function of that single electron each time you interfere with itself, right? in a sense, meaning that when the wave function pass through here, and as a caution, there's only this kind of picture of wave function as a real wave only work in for one particle. So like 3D, 2D picture only work for one particle. Why? Because this kind of continuous wave function we usually write as a function of the space coordinates, right? But if I have two particles, for example, I don't have individual wave function for each particle, but I would have joint wave function that is a function of 6 independent parameters. So you cannot write it. It's some function in a coordinate space, configuration space, and not like real space anymore. So the wave function here split into two partial wave. And then instead of just, classically here, the wave, the place that the wave would incident at the detector the most would be sort of like behind the slit, right, directly. So something like this. So two mountains, but then when you combine them together, it's sort of like just one bump. But here you will find different pattern. So the envelope, we believe that the envelope of this would still be the same as that. But now you have that fringes and white spots from destructive interference and constructive interference, respectively. So for the qubit analog, you can think of interference something like this. So if I have a 0 state and I apply the Hadamard gate, which for like classical scenario Hadamard would be more like a randomization, right? Because it sort of split whatever a deterministic state into something like 50-50. But here it's split into superposition. So the amplitude under the square root of 2 equal to this. But then if you apply Hadamard gain, for the quantum case, if you randomize the state twice, then it doesn't, well, especially if each state already uniformly randomize everything, the maximally, then applying it the second time is not going to do anything, right? But here, this will, again, using the same rule, this will split into the superposition, uniform superposition of 0 and 1. But then for the one state, I cannot do this, right? This does not split in the same way, right? Because of what? Because orthogonal states have to be mapped to orthogonal states also. And the way that the Hadamard works, that I have a minus sign over here, right? And then interference is that this and this cancel. So this is destructive interference. So the whole thing just go back to the state 0 again. Of course, for the classical analog, this does not happen, and I can write it as well. So let's see. Yeah, that's it. I don't want to write the whole thing, but here, so suppose that I already have want to write the whole thing down. But here, if I apply the Harnamat to this density matrix, well, we'll still do the same thing over here to each of the term. However, whatever terms that you get from each term will not interfere with each other. And so, for example, if this is just normalized correctly, that this is the maximally mixed state, then any unitary operation that you apply will do nothing to the state. Because it's just the identity, and then everything passed through the identity and hit with its inverse. So no interference here between different terms in the convex combination. And well, and one of the ways that this can happen, right, is by well, exactly the same circuit. So if I create an entanglement between the two systems, and then I only look at one of the qubits. For this one, let's look at the reduced density matrix. It will be exactly this state. And so over here, the state 1, 0 would not lose the ability to interfere unless you do something about the second qubit also. But this is like one of the simple model of sort of what happens in measurement, right? That I have a quantum system, and then I connect the quantum system, I correlate the quantum system to some kind of measurement device, which, well, if for the measurement to tell us something about the system, the measurement device, which, if you want to describe it quantumly, it has some kind of Hilbert space as well. The state of the measurement device has to be correlated, or in this case, entangled with the system. And then in real experiment, usually this system is not just like a clean single system. The information about your system will sort of like spread everywhere. For example, if you shine a light on your atom or whatever, and then your eyes are able to see the light, it means that the information about, like, for example, the position of the atom is already spread out in like the electromagnetic modes, like everywhere. You don't have control over. So usually those information are lost, and the interference is lost. So this is the way that you might have seen in when textbook discuss this double slit experiment before, like in finite lecture, that if I put a detector here, I have an eye here that can tell which slit the electron come from, then you also don't see it. You see this instead. And quantum eraser is a trick that people come up with to sort of erase the information in the other system to restore interference. This is the subject for next time. People, yeah, they do คนเขาจะใช้มักจะใช้ quantum eraser